Good morning all of you. So what we are going to discuss today is an extraordinarily important topic in modern physics, the so-called modern physics, and that is about the matter waves. So if you can remember what we have been doing in the last 8 or 10 lectures, we had a rather detailed discussion, an in-depth discussion on the particular nature of light. Although there was an overwhelming evidence for light to behave like a wave because of interference, because of diffraction and polarization, yet Planck found it necessary to introduce quanta of light, which were later called photons, and he associated an energy which is not proportional to the amplitude but which is proportional to the frequency, E equal to h nu. This idea, as we found, was taken very seriously by Einstein, who used this concept of quantization of light, where an incoming plane wave can be looked upon as an incoming particles, set of particles, all of them with the same frequency and an energy E equal to h nu, and Einstein was able to explain very satisfactorily photoelectric effect. As I told you, we spent a long time, many lectures discussing the experiment, discussing its conflict with the explanation coming from the wave theory. In fact, we showed that the discrepancy between the predictions of wave theory and the experimental observations were of the order of 10 to the power of 10 or 10 to the power of 12, gigantic discrepancy. And then we also showed how Einstein was able to give a satisfactory explanation by invoking the concept of a photon. So this was one of the most radical steps that a physicist took at the beginning of the 20th century in 1905, and that together with the Rutherford experiment and the Bohr model ushered in a new era, what we call as the era of quantum physics, and it is still continuing. Today what I am going to discuss is the counterpart of what we discussed in the case of the light. So what happened was that historically, so let us look at history. Historically, light had two possible explanations: particle, wave. The first one was advocated by none other than Newton, and the second one was advocated by Huygens. All of you have heard of Huygens principle. What later experiments did was to confirm the hypothesis of Huygens. For example, if light behaved like particles, then its speed inside a medium should be greater than the speed in free space. Whereas if it behaved like a wave, the speed of the wave in a medium, whenever it gets refracted, should be smaller than the speed in free space. That is something that you can experimentally verify. And then of course, as I told you, you have the phenomena of interference and diffraction. So all of them conclusively established that light behaves like a wave. Young's double slit experiment, Newton's rings, all these are examples of the wave-like nature of light. However, when it came to photoelectric effect, the wave explanation failed. Wave explanation failed, and what Einstein did was to invoke the idea that light is composed of quanta, where each quanta carries an energy h nu. So this is the energy carried by each quantum. So you essentially attribute a particle-like nature to light, and to imagine that photoelectric effect is essentially because of the absorption of individual quanta by the electron. In fact, one single quantum by the electron because of which it gets ejected. So what you do is to make use of energy conservation. As I told you, classically the energy of a wave would depend on the square of the amplitude, but here it is depending on the frequency of each quantum. Whereas classically frequency would only give you the degree of freedom, it would not have anything to do with energy. So that was a great thing. So in the world of waves and particles, we find an extraordinary dichotomy. That is, initially it appeared that there is nothing that relates waves and particles. Of course, there was an underlying picture that waves are collective phenomena coming because of the undulation of the molecules. So it is a collective phenomenon and it has no existence by itself. But what Einstein essentially showed was that what can be understood as an undulating phenomena of the underlying ether particles or any other medium molecules, even the molecular hypothesis was not established at that time, is that they can also be equivalently looked upon as particles, although not in every context. Because after all, interference, diffraction, polarization, all these require wave nature, and photoelectric effect, Compton scattering, and some more phenomena which we will see later, like Frank Compton experiment, they would require the quantum nature of light. So it is as if light has some kind of a double-phased existence. Sometimes it behaves like a wave and sometimes it behaves like a particle, and it seems to behave like a particle when the dimensions become very, very small. That is a crude way of putting. So if that be the case, we could ask a question. And what is the question that we are going to ask? If a wave can at times behave like a particle, let me explain that to you. A wave is an extended object because I speak of a wavelength and I speak of a frequency. It is extended in space. Whereas when I speak of a particle, it is something that is localized in space. Wave is extended in space, it undulates in time, whereas a particle is localized in space and it moves from one point to another as time progresses. And yet photoelectric effect tells me that what was a wave can actually start exhibiting particle-like nature. You are not looking at the wavelength, but you are looking at a particle-like nature because of the association of the energy. So if a wave can at times behave like a particle, is it possible? I am going to write everything clearly so that the so-called particles, classical particles, whatever we are used to, can behave like waves. Mind you, there were compelling reasons for us to attribute a particle-like nature to light because we were forced by experiments. It is not as if Planck or Einstein suddenly had a fanciful idea and then they said, okay, let us declare light to be made of particles. That is not it. We had the problem with black body radiation, we had the problem with photoelectric effect. So if that be the case, we should ask ourselves if there is any compelling reason why matter should behave like particles. The answer to that historically is rather quite complicated and rather different from the way we are going to discuss right now, because historically what happened was that 1905 was when Einstein gave an explanation of the photoelectric effect. So if I remember right, 1913 was when the Bohr model was proposed. Now in the Bohr model, all of you will study it in the coming lectures or you might have studied in your classroom already. What you do is to invoke very special orbits, and de Broglie realized that if you actually attribute a wave-like nature to the electron, that will give rise to, that can be looked upon as standing waves. And that is the reason why he proposed that matter can also exhibit wave-like behavior. In other words, there is no great distinction between matter and waves. They are both manifestations of the same underlying substance. And de Broglie's hypothesis was poised at the right moment in history because 1924 was when he proposed the matter wave hypothesis, and 1926 is when Schrodinger wrote his famous Schrodinger equation. But that is not the path that we are going to take in this lecture, because in your textbook the de Broglie waves have been introduced immediately after the photon concept of light, the particle nature of light. So what I will try to do is to motivate you to look at the wave aspect of matter from an aesthetic viewpoint, and later when I start discussing Bohr model, I will complete the argument by showing how it can be a standing wave. So in other words, so far what we have done is to look at the historical development and follow that even in our presentation. But now we are going to reverse history. We are going to discuss de Broglie waves first, and then we are going to discuss how he was motivated by the Bohr model. So these were indeed very, very revolutionary. So if you look at the slide which I have here, you can see the picture of de Broglie, and let us see what is it that de Broglie did. So as I told you that we want to look at the whole phenomena in an aesthetic manner. So what is aesthetic? Aesthetic is whatever pleases our mind, and in this case it is our intellect. It is not our sensory, it is not our eyes, ears or tongue or touch, it is our intellect. And that can be summarized in a single word, namely symmetry. So what is the symmetry that we want to establish? We had a very clear division of the world between wave-like phenomena and matter, corpuscles and waves, to put it in the old language. Now if waves started behaving as corpuscles, probably there is a symmetry which says that under certain circumstances particles will also start behaving like waves. How exactly the wave-like nature will emerge from localized particles is a different question altogether, because after all we have not answered how exactly the particle-like nature will emerge from the wave either. All that we have done is to make a hypothesis in order to understand an experiment, give a plausible explanation of the experiment. So a deeper understanding of what the connection between a wave-like behavior and a corpuscle-like behavior, that will come at a much later stage when you people take up more advanced courses in quantum mechanics. When you go for your graduation, it is not a matter for the 12th standard course. But however, it does not harm us to establish symmetry between what I shall call as classical waves and classical particles. Classical waves get quantized and they show quantum behavior. There are quanta, corpuscles, which behave like particles. So probably classical particles can behave like quantum waves, which we shall call as matter waves. So that is the statement that we want to make. So the most important motivation for that is symmetry. Now symmetry is a vague idea. I want to establish parity. I want to treat them on the same footing. Now I need a reasoning, and the reasoning that de Broglie employed was by analogy. We have to make use of analogy, and the way we make use of analogy is not a trivial thing. You have to meander our way. We have to find our way through the maze carefully, and let us see how it comes about. So this slide contains something more on analogy. I have collected it here, and I am going to discuss it at great length, what the consequences of this are for matter waves at the end of the lecture. So let us go back to what Planck and Einstein did. Planck associated an energy E with every frequency nu. So I am also going to write that down so that it settles clearly in your mind. So nu is given and energy is deduced. That is the Planck hypothesis. And this is completely non-classical. However, classically there is another relation between frequency and wavelength. We are looking at a monochromatic light, all the light having the same frequency, okay? And what is that relation? And that is V equal to nu lambda. V of course is c for light in free space, the speed of light in vacuum, which is 3 into 10 to the power of 8 meters per second or whatever, that is what we have. So what we are writing is now a relation between nu and lambda, everybody knows that, therefore my lambda is given by c by nu, that is what I have. So if I were to write it in terms of energy, my nu is E by h, so 1 over, so nu is E by h, 1 over nu is h by E, so I am going to write lambda is equal to h c by nu. I am sorry, h c by E, that is what we are writing. So that means not only do we associate a frequency with the energy or energy with the frequency, we are also associating energy with the wavelength. Now, if you people go back and remember our rather lengthy discussion on photoelectric effect, I argued that the momentum density and the energy density are related by a factor of c. So what did we say? Let me go to the next slide. So if I write down the energy density of a monochromatic wave, let us say a plane wave with a given frequency, then this is related to the momentum density by a factor of c. What is energy density? That is the total energy in a given volume, that is my energy density. And what is my momentum density? That is the momentum carried by the wave in a given volume. These two are related by a factor of c, and this is dimensionally correct. So this is my energy density and this is my momentum density. Now what is energy density from the Planck viewpoint? From the Planck viewpoint, it is nothing but the number density multiplied by h nu. Each quantum is carrying an energy h nu, that is the energy of each quantum, and they multiplied by the number density, that is what I am going to get. And what would be my momentum density? It is again the number density carried by momentum carried by each quantum multiplied by c. So in other words, this p is the momentum carried by the quantum. To be sure, this analysis of connecting momentum to energy was not done by Einstein in the photoelectric effect, because nowhere did he bother about the momentum of the photon. He only worried about the energy of the photon. Only energy was matched, balanced in the photoelectric effect explanation. Momentum was not taken into consideration at all. But now, if you look at this, you can actually cancel this relation and you have got a beautiful relation. The energy of a photon carrying a frequency nu is nothing but p corresponding to that frequency into c. So this is the relation between the energy of the momentum, energy of a photon and the momentum of a photon. This is completely different from what we find either for a massive particle in relativity or in non-relativistic case. Is that okay? For example, you write E equal to p squared by 2m as a relation between the momentum and energy for a particle. But here what we have is E nu equal to p nu c. Therefore, what we have is that as the frequency keeps on increasing, my energy also keeps on increasing, my momentum also keeps on increasing, but in such a way that it always travels with the same speed c. Contrast this with a massive particle where as you keep on increasing the energy, the momentum also keeps on increasing, but then the velocity also keeps on increasing. You cannot increase the momentum of a massive particle without increasing the speed, but here there is a very beautiful way of looking at it. You have E nu equal to p nu c. This is very, very important for us and we are going to make use of that. So if we did that and I substitute back into the equation, Now I can also write the relation P equal to h by lambda. So E equal to h nu is what Planck plus Einstein used. But if you make use of the energy density momentum density argument, not only is my quantum carrying an energy nu E corresponding to the frequency nu, there is a momentum corresponding to the wavelength. It is an entirely different matter at this point that lambda and nu are of course not independent of each other, because lambda into nu equal to c. That is not very important for us at this point, although I used it in my derivation. I will tell you why. What de Broglie did was to take this as a fundamental relation, And this is non-trivial. So the message that I am trying to convey to you is that it is not as if de Broglie simply extended whatever was known in the realm of electromagnetic waves to matter. He had to choose, whereas in the case of electromagnetic wave, E equal to h nu was the fundamental starting point. For de Broglie, P equal to h by lambda was the starting point. So what is the de Broglie assertion? So let us write the thing. De Broglie conjecture, let us call it. De Broglie conjecture was that P equal to h by lambda is a universal relation. So what does universal mean? Universal means it holds for all waves and all matter. It holds for all waves and all matter. This is a fundamental relation. The only freedom that you have is in choosing the form of P. So P can be mv, or it can be mv over root 1 minus v squared by c squared. mv gamma. This is relativistic. This is, the earlier one is non-relativistic. Let me write that more carefully again. P Newtonian is m naught v, and P Einsteinian relativistic is m naught v over root of 1 minus v squared by c squared. So to conclude whatever we have done so far, to summarize, what we are saying is that de Broglie hypothesized, he conjectured that P equal to h by lambda is valid even for particles. So in the case of Planck, frequency was known and energy was deduced. In the case of de Broglie, what is happening? You know the momentum and you are deducing the wavelength. That is extraordinarily important. In other words, P is the input and lambda is the output. So this essentially is a de Broglie hypothesis, and this requires experimental confirmation, because we have tried to treat both waves and matters symmetrically, and we have also deduced the relation P equal to h by lambda. All that we are asserting is that it is not only peculiar to light, but it is also valid for all waves and matter. This is the statement that we made. So this slide essentially contains the summary of whatever I told you. So two questions that we asked without explicitly mentioning was that how important is the de Broglie extension and how non-trivial it is. These are the two important questions that we have to ask. So what are the fundamental relations that we are making use of? We write lambda equal to h by p. Meaning if you give me P, I will give you lambda, and who is going to give you P? It is either Mr. Newton or Einstein. Newton will tell you that P is equal to mv, and Einstein will tell you that the relation between energy and momentum is given by E squared equal to P squared C squared plus m naught squared C to the power of 4, which is the same as writing P is equal to mv gamma. The two relations are the same. So I have written it not in the way I wrote on the sheet of paper in this particular form, because what matters to us is really the relation between energy and momentum. We can always deduce what the velocity is given the relation between energy and momentum. That is going to be important for us at the end of the lecture, and that is why I wrote it in this particular form. Okay. So we have made a conjecture that matter can also exhibit wave-like phenomena. Now what do we mean by matter? So one thing that I can do is to make an estimate of what lambda is by h by p. I am not going to work it out for you. So anyway, it is given in your textbooks. So what you can do is to take your matter to be, let us say, a tennis ball. So imagine a very, very fast bowler who is bowling the ball at, let us say, 100 kilometers per hour or 120 kilometers per hour. That is a very fast ball that is going around. And you know what the mass of a ball is? Maybe 100 grams or whatever. If you put in and you find out what this lambda is, this will turn out to be an incredibly small number. So this number could be of the order of 10 to the power of minus 30 or 10 to the power of minus 34 centimeter or whatever. This number is so incredibly small that it cannot reveal the wave-like nature of the object. You want a reasonably large wavelength in order to realize that it is a wave. If the wavelength becomes very, very small, it almost becomes like corpuscular. So we don't want to get into that situation. We want a fairly large wavelength. So in order to get a large wavelength, what is it that we have here? We have P sitting in the denominator. I can control velocity all right. I can even throw my ball at a slow speed, but my m is so large. Even for very, very small speeds, what is going to happen? My lambda is going to be quite small. So in a way, I gave you a wrong analogy. I am very sorry. What I should be saying is that even if my tennis ball is moving very, very slowly, I just slide it on the ground, my lambda will be very small because mass is very, very large. So I should look for very, very light particles. I should look for very, very light particles, and those particles should actually be able to interact with something in order to show a wave-like behavior. Like for example, it may be a double slit experiment, or it may be a diffraction, as we are going to discuss in a while, and the best candidate is electron, because electron has a rest mass of 0.5 MeV by c squared, which is very, very small, and therefore if I can actually make use of electrons of varying energy and therefore of varying momentum, then I should be able to verify whether the de Broglie hypothesis is correct or not. Of course, we are going to work in the non-relativistic regime. Therefore, my momentum will be nothing but m into v. That is what I will have, and mass is given by 0.5 MeV by c squared, and this will be nothing but 0.5 MeV into v by c. So this will be your momentum of the particle, and it will not be too large. Therefore, my lambda can be large enough. If p is small, my lambda can be large enough. De Broglie did not stop at the hypothesis. He suggested that wave-like nature of electrons can be seen in diffraction from crystals. De Broglie was fortunate that by that time the crystal structure was known. It was supposed to be a regular symmetric object, and Bragg the two Braggs, the father Bragg and the son Bragg, had actually obtained the condition for diffraction, and that is illustrated in the slide here, which I would like to explain to you. Now, if you look at this slide carefully, what we have is a periodic array of atoms, and you are going to send light. This argument is for light, and we want to make use of the same argument for the electrons also. Now, what is going to happen is that when you send light of the right wavelength, I am going to come to that in a minute, what the right wavelength is, then what happens? These light beams get reflected by successive planes, because every crystal can be looked upon as what? Arrangement of atoms in each plane, and then there is a plane below that, there is a plane below that, and the separation between the planes is what is indicated by D here. So, let me illustrate that in bigger letters here, if it is not visible to you. So, what we have is, I am exaggerating it. So, imagine the atoms to be arranged in an array, and I am saying that the distance between them is D. That is what I have here. Now, what happens? Let us come back to this slide here. If you imagine that a ray of light is coming, it can get reflected either in the top layer or in the bottom layer. So, these two atoms, lattice points are shown, and then when they get reflected, you can see that there is a path difference and there is a phase difference. So, let me again illustrate that in big letters here, big picture here. So, I have this. So, here is a light ray which comes here and gets reflected here, and there is another light ray which comes here and gets reflected here. So, this is my upper ray and this is my lower ray. So, everyone agrees that the upper ray traverses a smaller distance compared to the lower ray, because it has to reach the plane and it has to come back, and we are asserting that this is D, and I have to design my theta, this is my theta and this is my theta by law of reflection. Angle of incidence is the same as angle of reflection, that is what I have, this is my theta. So, a very simple trigonometric exercise will tell you what is the extra distance that is travelled. The extra distance travelled is nothing but 2d sin theta. That is what we are showing here. So, now if I therefore look at this extra distance that has been travelled by light, there is a corresponding phase difference. Now, what you are going to do is to demand that there must be a constructive interference. Please remember, when we started discussing evidence for wave-like nature for light, we actually worked out the interference condition, and the condition is that this must be an integer multiple of lambda. So, if a wavelength of a certain frequency is hitting a crystal and it is getting reflected back, then what we find is 2d sin theta equal to n lambda for constructive interference. And what is the condition n? N should be an integer. So, in other words, for a light of a given wavelength, if you for example keep on rotating the crystal so that you can change the angle, or you can rotate your detector so that you can look at the change of the angle, because a wave is coming like this, there should be specific values of theta at which you are going to find a peak, maximum constructive interference, and therefore the intensity will peak there, and that sin theta will be given by n lambda by 2d. So, theta will be sin inverse n lambda by 2d. N equal to 1 will give you the first maxima, n equal to 2 will give the second maxima, so on and so forth. We should be able to find that, and this is exactly the Bragg condition. So, it should interest you to know that both the father Bragg and the junior Bragg got a Nobel Prize for this very important piece of work, and von Loewe actually recognized that if you are given a crystal like sodium or copper or any of the metals, okay, then the right wavelength or the frequency in order to see this kind of a diffraction is in the X-ray region. That is your famous X-ray diffraction, and today it is an extraordinarily important tool for us to determine the crystal structure. So at this point I should tell you that what I have shown you is a very simplistic view D. Depending on which phase of the crystal that you are going to look at, this D can change. It will come with 3 indices H, K, L. So people generally say 1, 1 plane, 1, 1, 1 plane, 2, 2, 2 plane, 1, 1, 0 plane, so on and so forth. So by looking at the crystal at various angles, you should be able to determine the crystal structure if you know the wavelength very precisely. And even today, X-ray diffraction, XRD as it is commonly called, is a very, very powerful tool, and this is what de Broglie wanted to make use of. So de Broglie made the hypothesis. He was a theorist, and he wrote his thesis on matter waves. Not only did he get a PhD, he also got a Nobel Prize very soon. So it is one of those rare cases which happened at the around 1920s when all the theses got Nobel Prizes. Heisenberg, de Broglie, Dirac, all these people did their thesis work in order to get their Nobel Prize. But the 2 gentlemen who did the experiments, I am showing you their picture here, Davisson and Germer, these people were not working in a university, they were in Bell Labs, and they were doing experiments, and these people verified the de Broglie hypothesis in 1927. So what are we saying? 1924 is the matter wave hypothesis, and 1927 when it was verified on nickel crystal. It is not that people took de Broglie hypothesis very seriously, but it also did not encounter the kind of very harsh criticism that Einstein's belief in photon encountered, because meanwhile Compton scattering had been very well understood through the concept of a photon, and Bohr in his Bohr model had argued that when an electron makes a transition from an excited state to higher excited state to a lower excited state or to the ground state, the radiation emitted actually obeys the Planck law, E is equal to h nu. So in that sense de Broglie was fortunate. Therefore after he made the hypothesis in 1927, Davisson and Germer performed a very beautiful experiment which verified that. So this is the famous paper that everyone alludes to, which was published in Physical Review, but subsequently in 1928 they published another paper in Proceedings of National Academy of Sciences, where they again verified the result, and they wrote a detailed description and critique of both their experiment and the de Broglie hypothesis. At this point I want to take a digression and I want to tell you how this experiment came about, because really speaking Davisson and Germer were not into the business of verifying de Broglie hypothesis. They were interested in verifying something else, and some time back, maybe a year back or whatever, when they were doing an experiment, there was some glass tube containing air and some liquid, and because of high temperature the tube exploded, and they had a crystal which was nickel actually, but it was polycrystalline, it was not a single crystal. So the whole thing fell on the crystal and it created quite a mess. But Davisson and Germer were not to give that up. They wanted to get the crystal back and remove all the fluid that had accumulated on the surface, that had been absorbed on the surface. So what they did was to carefully heat, cool, so that all the liquid or other gases that had been absorbed would be removed, and it took them quite some time, months actually, but their patient work gave them something extraordinary, and they suddenly discovered that what they had got was actually a almost perfect single crystal. It was not a polycrystalline quantity, but it was a single crystal. Single crystals are not easy to get. Today of course we know how to get extraordinarily good perfect single crystals like for silicon or things like that, but not so in 1920s. And they verified that it was a single crystal by making use of the Bragg diffraction rule. So they identified the 1-1 plane, 1-1-1 plane using the von Laue rules. Then what they did was to direct electrons towards the 111 plane, because they thought electrons are particles, so they would get scattered and some of them would actually pass through, and they expected them all to be channelized in some particular direction, like it would happen in the case of a particle nature. So they certainly did not think that they were trying to verify, either prove or disprove the de Broglie hypothesis. They were working under the conventional assumptions of electron behaving like a particle. After all, that is what cathode rays tell you, but what they found was something really extraordinary. So what exactly is the experiment that they performed? So if you look at your slide, you find a schematic explanation, schematic diagram. So what does the schematic diagram tell you? The schematic diagram essentially tells you, so you have to look at a few things. There is an electron gun which produces an electron beam. Now the most crucial thing here is that you should be actually able to accelerate, you should be able to vary the momentum, that is what you should be able to do. So what you do is to put a voltage difference accelerated by a certain voltage. Then what happens, as it accelerates, its energy increases, its momentum increases, and as the momentum increases, its wavelength changes. It starts from a small value to a larger value and starts going to a smaller value, so it is then under control. Then you see at that angle theta, there is a nickel target, my electrons are getting reflected, and I put a movable collector. So the movable collector simply does not try to distinguish between individual electrons, it will simply ask how much charge has been collected. How much charge has been collected will be known by looking at how much current flows. So the current is a measure of the intensity, and that is known through the galvanometer which you show here. Of course, you do not want loss because of collision with the air molecules, you do not want any disturbance for the electron beam, you should be fairly monochromatic. I should not use the word monochromatic, you should be fairly monoenergetic, therefore mono momentum. So there is a vacuum chamber, that is what you have there, and then what you do is to move your galvanometer, measure the current or look at the deflection. The deflection is a measure of how much of current is flowing. You all have done experiments with your galvanometer and you look at what it is. So this is a very beautifully done schematic diagram in your NCERT book, and this is exactly what Davisson and Germer did, but what the next slide shows is actually the apparatus itself. So this is the 1927 apparatus that those people used. It is from Physical Review in 1927. Physical Review was then still a rather young journal, because most of the great papers were published in European journals. So you see there is something called G, which is the electron gun, and T is the target. There is a voltage difference between them, and what we call as C is the collector. And this collector actually moves along that arc, which is rather hemispherical, and you start looking at it, and the rest of it is all controls. How you move the thing, there are these springs, there are these levers and whatnot, they tell you, and what they did was to actually perform the experiment very, very carefully. And the most important thing for you to know is that the target was a nice single crystal, and for those of you who are a little bit familiar with crystallography, what they were looking at was actually the 111 plane. If you do not understand the meaning of what 111 plane is, never mind about that, but this is the apparatus. Okay. Now these are the experimental results. That is something that we want to discuss at some length now. So probably before I can show that here. Your book tells you that the experiments were done sometime between 40 to 64 volts. So the voltage drop was varying from 48 to 64. So if you assume that the electrons started at very, very low energies, almost at rest, what is the energy gained by them? Either 48 electron volts or 64 electron volt or something in between them. Now what you do is to say, let us say 60 electron volts, equate it to p squared by 2m, and then find out your p, then you make use of your de Broglie hypothesis and find your lambda. So essentially the message is that when your energy is changing from 48 to 65 volts, the momentum is correspondingly changing, and I am looking at the scattered cross section. That is what we are looking at. And in this figure, you can see there are two such figures. What have you done? You have fixed your voltage and you are changing your azimuth angle. Your azimuth angle is something like the theta that we have written. There is a mismatch of the notation, and you see that there are very well defined peaks both for 65 volts and for 54 volt. 54 volt corresponds to larger wavelength, 65 volts corresponds to the shorter wavelength because the momentum has increased. And what Davisson and Germer found in their experiment, contrary to their expectation, was that this peaks, that is where the maximum constructive interference is taking place according to de Broglie, agrees very well with what? Agrees very well with the de Broglie formula, P equal to h by lambda. That is what they found out, and this was indeed a landmark experiment. It was a path breaking experiment which established the wave-like property of matter. This is a figure which they published in the next year, 1928. Here what they have done is to plot it against square root of V, and you should explain that. So let me do a little bit of simple algebra which is not too difficult, and let us come back to this slide later. So what I am trying to tell you is that P squared by 2m is my energy, and that is nothing but the charge of by electron multiplied by the voltage. That is what I have. So my P is therefore given by square root of 2m E into the voltage. That is the most important thing. Now my mass of the electron is known, my charge of the electron is known, my 2 of course is a number, therefore this is some constant into root V, where V is the voltage drop. And what is de Broglie telling us? De Broglie is telling us that this is equal to h by lambda. De Broglie is telling that it is equal to h by lambda. Therefore, if I transfer it, my lambda is nothing but h over k root V. This is the hypothesis. So let me repeat that expression here. Lambda is equal to h over k root V. K is known, h is not necessarily known. We will come to that in a minute. And our constructive condition was that n lambda equal to 2d sin theta. So which is equal to n into h over k root V. That is what we have. So what you are now doing is to look at the variation of sin theta with respect to root V, and not only that, you are trying to determine this slope h by k if the de Broglie hypothesis is correct. So in other words, not only should you be able to find the peak at the right position, but you should also be able to fit it to the de Broglie formula, and what Davisson and Germer found was that it was indeed correct, and that is the reason why they are plotting it as a function of root V. Okay, all that you have to do is to transfer it to the right hand side, and they are plotting the intensity peak as a function of root V at a fixed angle. That is what you are doing. The angle is fixed. Is that okay? And they found a beautiful confirmation for the maxima. In fact, there is a confirmation for the minima also, which corresponds to n plus half, where n is an integer. So in their paper, they mention that to their great surprise, they found that it was agreeing, their experimental results were agreeing with the de Broglie hypothesis. Now you may ask, how good is this experiment compared to the modern days or X-ray diffraction? So I am showing you a number of figures. Look at these peaks. These experiments were done in 1925, 26, 27, that is when the experimental techniques were not completely developed. That is what we are looking at. Now if you look at a modern day X-ray diffraction experiment, our diffractometers are much more advanced today, our crystals are much better single crystals, you see these sharp peaks, which is almost in quite a good agreement with the peaks that we are seeing here. Okay, so that is the X-ray diffraction result, and this is my de Broglie result. Modern day experiments, of course, do show such a sharp feature. Probably in the next class I am going to show you some of them, but basically what we are saying is that we are now doing something very funny. We are making use of the wave nature of the light to support and substantiate the hypothesis that particles can show wave-like behavior, whereas in the photoelectric effect we just did the opposite. We said that light actually behaves like particles. So we are in an extraordinary situation where we do not know whether something is a particle or a wave unless you give me the circumstances under which I am going to look at. So that is a message that we are going to look at. So you see, these features are extraordinarily nice, and this is what we have. So these are the mandatory numbers which I should show you. These are there in your textbook, and there are all these very simple problems which you can do now. Given the diffraction peak, find the wavelength, or given the wavelength and the diffraction peak, find the lattice spacing, so on and so forth. But in the Davisson and Germer experiment, as I told you, it was between something like 48 to 64 volts. The maximum occurred at 50 degrees at 54 volts, and the corresponding de Broglie wavelength is 0.165 nanometer, which is close to what you find in the X-ray range actually. So this is quite an interesting and a spectacular demonstration of the wave nature of the electron. So far what we have done is to give a free rein to our imagination. Even if you assume that, okay, there is a Bohr model and I want to produce a standing wave, so on and so forth. But one thing that this kind of an analysis and this experimental verification does is to throw up a number of questions. A wave is characterized not only by its frequency, but wavelength, but it is also characterized by its frequency. Now what I have done is to associate a wavelength with the momentum, but what about the frequency? And if there is a certain frequency, what is the velocity of the wave? It is very tempting to imagine that, you know, the wave with which the wave associated with a particle, let me put that way, the wave with which the wave moves when it is associated with the particle should also be the velocity of the particle. But we are not at liberty to draw such a conclusion. So here are the questions which are shown on this slide for you. What is the frequency? What is the relation between frequency, wavelength and speed? So unless we answer this question, we have not completed our task. So this is something that we should know, although it is technically not in our syllabus. So what we shall do is to start looking at them at some length. So what we are going to ask is for relationship between frequency, wavelength and velocity. We need to work it out and let us see what we are going to get. What I will do is, since I am running out of time, I will give all the basic expressions for you, both relativistically and non-relativistically, and then we will see that we are going to run in trouble. So the question is how we are going to get out of trouble, and there you have to know that there is a distinction between what is called phase velocity and a group velocity. Group velocity is something that you are not exposed to. So I will introduce this concept, although it is not technically in your syllabus, and I will show you how you can recover the relations. So the important equations that I am going to make use of are obviously P equal to mv equal to h by lambda, and d is equal to p squared by 2m, and what we may like to do is to write it as h nu. I will put a question mark on this, but I have another relation we should not forget, v is equal to p by m. We should not forget this, and this is nu lambda. I put a question mark. That is something that we have to do. So what I will do is, I will ask you to look at all these three equations, play around and try to see whether you get a consistent set of relationships between energy, momentum, velocity, wavelength and frequency. So, you please play around with these symbols, is that okay? I have put 2 question marks because this has been established experimentally, and in the next lecture what we are going to do is to take this further, analyze these relations. I will also write down the corresponding relativistic equations, and then after doing this we will start a discussion of the great Rutherford experiment. So, let us stop here. Have a good day.